So I'd imagine that probably all of us have worked on one of these data sets at some point. Now, conversely, we have these kinds of data sets, things like cancer detection, electronic health records, drug development, and I'd imagine that most of us haven't worked on these sorts of data sets. There definitely aren't tutorials for them. They're siloed away in various different private data sets, databases, and they're just really hard to access. Like, why is it that we can't just pip install health records? Like, why is this orange group so much harder to work with than this blue group, despite the fact that these are, some of the most important things we could be applying machine learning to? Well, it's because the data is sensitive, and so it's really hard to have both privacy and accessibility. How do we encounter these problems? Well, if you've got, say, hospitals, and they've got their own data sets, maybe they don't trust each other, or for legal reasons, they're not allowed to share their patients' data with each other. But maybe they want to do some analysis of this data, so they can find some trusted analysts, so maybe they hire some people, or they get consultants. But they have to trust these people if they give them access to the data. They have to go through ethics clearance. There has to be kind of review. It's a really slow process. Now, if these people want to do anything more than kind of just basic results, they might need some computational resources like GPUs and things like that to be able to train, say, deep models. Well, the problem here is that now, like, you either have to take this data then off-site, so you have to take it, put it into the cloud on AWS or Google Cloud or something like that, or you need to go and install this hardware at the site of the data, and the sysadmins there are not going to want you just plugging in hardware there. Both of those are going to impose some either trust issues or general vulnerabilities and obviously huge costs and inefficiency. And you might produce a model with this, but this model is potentially vulnerable. If you prod it in the right way, you can get it to regurgitate its training data. So you can't even release this model. This model has to be kept super secure. And then finally, you can get some public results that can be released. And the real problem is that an adversary, along any step of the way here, even in the future, an adversary could come along and attack all of these points, right? Like anything that's happening at the hospital, can be attacked. It can be attacked via the analysts directly or via the computational hardware when it gets into a third party. But we know the models can be attacked. And there's this problem of naive anonymization, right? So you think, okay, cool, we just block out everyone's names and their ID numbers, and then it's fine because people don't know who it is. But it doesn't take that many different data points about someone combined with information just that's publicly available on the internet to de-anonymize people. And we've seen this time and time again with some very high stakes data all over the world where it's been naively anonymized and released. And then, a few years later, someone's come along and easily been able to re-identify everyone. And we don't know what information is going to be available in the future or what's out there currently. So without making any privacy guarantees, it's just really hard to know that anything like this is going to actually work. All right, so what approaches do we have that might help us get around this? Well, the first one is kind of an oversimplification of just the general class of encryption-based methods. At your sensitive data site, we're going to call them hospitals from now on, you would have a data set that you have that's sensitive, patient records, let's say. You apply some kind of encryption algorithm to it. Now you can send it off-site to some kind of server. It's still encrypted along the whole way, which keeps it somewhat secure. And now you have to do encrypted computation on this. The problem with this is that it only allows you to do kind of simple operations. You're getting kind of things like averages and maxes and minimums. Right? It's very simple summary statistics most of the time. It also makes no privacy guarantees, right? Like in the future, we might just have better computers or quantum computers that can break these encryptions standards. And so it's not really future-proof. Right? Anything that can be locked can be unlocked given sufficient technology. But it does allow you to do your computation off-site, which is an advantage. Right, the next technique, and the one that's going to be the focus of much of the study, is differential privacy. So it starts off in a similar way, where we have some sensitive data set, but now what we do is we add noise in a very special way to that data set, and we keep track of exactly what noise we've added. So this is often like Gaussian noise or Laplacian noise. And we now get a version of this data set that's noisy in a way that specifically tries to hide the sensitive information while not interfering too much with the dataset. Now you can send this off-site and go and get some results from it by just knowing what noise was added and being able to kind of subtract that in a meaningful way without compromising the individual records. So it still allows you to get sort of high-level information. And so this is trustless. It enables public release. It gives you strong privacy guarantees because the actual amount of information is quantified, but it does require some on-site computation, and it might obviously lose data quality in some cases. And then you've got another of the common approaches now, which is federated learning. And so this does kind of distributed modeling. So you train a model of some kind on site. Then you share these sort of partial models to some trusted third party that then combines them to produce a final model. And so instead of sharing the data, you kind of share the model weights. But this requires a lot of on-site computation, quite a lot of power to train models. And while it does support arbitrary algorithms, it relies on the central server being trusted. And obviously, these models are still vulnerable to attacks. Right, okay. None of these are actually mutually exclusive, and by combining kind of parts of them, you can get some really interesting things. And by sort of focusing on this differential privacy and the valuable things it affords, we can get to this next idea, which is DP synthesis. So similar to differential privacy, we're adding controlled amounts of noise, but instead of adding it into a data set, we add it while training a generative model. And what this allows us to do is some really cool things. We can now either release the model, or we can use the model directly to generate data and then release that data. Right? So this gives us so many options. We could also just release this data publicly because it's a totally trustless system. Again, this also supports arbitrary computation, so it can then be used to generate models or to just get summary and analysis statistics. So this obviously is going to require lots of on-site computation to do the generative modeling, but thereafter it gives us a lot of flexibility, and it's totally trustless and future-proof for reasons that we'll get into shortly. Okay, what kind of generative models do we have? So these are two of the most common. You've probably heard of these before, have some understanding how they work, so here's a quick recap, just in case. We have some data that we put into a variational autoencoder. It compresses down the information into a latent space, and then you have a second network that is going to decompress the information back up into the original space and try and recreate the data set as best as possible. In the case of a variational autoencoder, this is a multivariate normal distribution, and that's really great because it means that we can sample from it, which allows us to synthesize data in the future. By comparison, we have the GAN, the generative adversarial network, and you've got two networks that kind of play this game with each other. You start with a multivariate normal distribution, and your generator uses that to just make something. And then what we do is we give that something and some real data to this discriminator network, and its goal is to try and tell which is which. And then we tell it whether it's right or not, and it learns to get better at telling these apart. But it also gives that information back to the generator that learns to get better at faking the data. And they play this game, and we kind of biased it in favor of the generator so that at the end, the generator is really, really good, and this data is really close to the real data in distribution. And then for our purposes, we can kind of just throw away the other components and just be left with this kind of conserved structure here, which is, latent probability distribution we can sample from, put these values into some kind of network that generates samples that followed the original data distribution but are totally synthetic. Okay, what is differential privacy? Differential privacy is a system for quantifying like the amount of information in data and making guarantees about how that will change over time. So if we have a data set, we can look at its neighbor, and the neighbor of a data set is just the data set, but it differs by exactly one record. So X and X prime here are neighboring data sets. We've just deleted someone from the data set here. What differential privacy is all about is saying if we have some privacy mechanism, and this could be a learning model, this could be a function, this could be whatever. We have some mechanism here. If this is differentially private, then some adversary who doesn't have access to the original data sets has no way of knowing which data set they're looking at here, if they're looking at X or X prime, once it's gone through this mechanism. And so what this tells us is they have no way of knowing if this record or this person was included in that data set, so they can say nothing about that person. If this property holds true for every possible record in this data set, for any possible data set, then the system is differentially private. And so we have kind of two parameters to play with here. We've got epsilon, which is the privacy level, and we've got delta, which is the probability that it fails. And we set this to some very, very small amount. And this is just to like make the problem kind of tractable because in a million years, it's unlikely that that's ever going to happen. And if it does, it's only for one record. But this epsilon is kind of the main thing. All right, well, this is great. And this leads us to the most important property for our consideration here, which is this post-processing guarantee of differential privacy. And what that says is if we've got some mechanism, say a data set, a deep learning network, whatever, and we can show that it's epsilon delta differentially private, then anything we do with that, whether we make a data set out of it, where we train a model on it, anything we do will also be epsilon delta differentially private. And that's this amazing property because that gives us the future proofness. It means that the information is totally bounded. No information from outside sources in the future, no other future technique will be able to undo this. We have a proof that this is guaranteed in the future, which is a really amazing guarantee and what makes differential privacy so powerful. Okay, but how do we apply it to deep networks? Well, it's actually quite simple. What we do is when we're doing our gradient updates in our stochastic gradient descent or any other kind of similar optimization, what we do is we clip the gradients, so we kind of cap the maximum magnitude, and this sort of stops them overfitting to specific examples in the data. And we also add some Gaussian noise, which is another factor that's going to stop them from regurgitating exact examples. And so instead of doing anything to the data set, we're actually just doing it to the gradients during training. And this is how we apply differential privacy into the sort of domain of deep learning. And so in the case of a GAN, we'd only have to apply it to the discriminator because that's the only thing that actually sees the real data. And so everything kind of behind this will inherit from that post-processing guarantee. And so what this looks like in practice is we set our epsilon and delta, what we call our privacy budget, based on sort of how sensitive the data is and how much privacy we're willing to sacrifice for our goal. And then what we do is we just say, while we're still within that privacy budget, we run this differential privacy gradient descent, and we then use this privacy accountant that's going to quantify how much we've spent while doing this gradient update. And we just keep track of these epsilon and deltas until they hit our privacy budget, and then we stop. Okay, sounds great. What's the problem? Well, in practice, what this means is that you get a trade-off between utility and privacy. This is like the quality of your data and how good it is for downstream tasks like prediction, things we actually care about doing with the data, and the amounts of privacy that we're able to preserve. Right? Because the more noise you add into the data, the more you obfuscate it, just the lower quality model you tend to get. And so you fundamentally get this kind of trade-off where, like, to get better quality, you need to have lower privacy or vice versa. And that's a pretty bad situation. So the goal of my thesis is to try and just increase the area under the curve here, is to make this less of a bad trade-off. Okay, how do we attack this? Well, there's two ways to maximize it. The first is to make privacy more efficient. So for any given privacy budget, can we just get a greater number of useful computational steps out of it? Right? So can our privacy budget be more efficiently spent to do good deep learning in a generative context? That's the first approach. And then kind of the other side of the coin is saying, can we just do more efficient modeling? Fewer computational steps, and therefore use up less of our privacy budget. And so these two kind of are complementary directions that push together to shift this curve. All right, how is this actually going to be attacked? Well, these are the directions that I think are promising so far from everything I've seen in the literature and my intuitions. So firstly is the kind of theoretical avenues. The first is to reformulate differential privacy. And the reason you might want to do this is because all of our privacy bounds are estimates. And so when you're doing gradient descent with differential privacy, you are estimating how much privacy is being lost given the theory that we have. And so you kind of have an upper bound and a lower bound, but if we can make those bounds tighter, more accurate estimates of the true value, then that gives us a lot more room to play with our privacy budget and get more utility out. And Rényi differential privacy, which is based on Rényi entropy, is one way that this has been attempted in the past, and it does have some promising results, which means there might be future ways this can be done to an even greater extent. Well, another thing we can do is just try and combine the loss function with differential privacy. Differential privacy wasn't originally formulated for deep learning, and so it's not tightly integrated with utility in terms of the loss function. And so there might be a way to integrate these two in a way that allows us to maximize both simultaneously using gradient descent. Then in the empirical side, there's just general advances in deep learning, and most of them haven't yet trickled through to this domain, right? So there's a lot of people working on just making deep learning better, but relatively fewer people working in differential privacy or generative synthesis. And so, one that has creeped through is using Wasserstein GANs, but there are other advances that haven't yet trickled through, and just applying those might make the networks just more efficient and therefore use up less of the privacy budget or get higher quality results. And so that's just something that's worthwhile doing. And finally, it might be possible to do something that's very domain specific. So do privacy focused architectures. So one example here would be like an auxiliary GAN, where you have two discriminators, and one could look at how good of a recreation is it, like what's your utility, and the other could look at what privacy cost it's coming at, and so you could maybe simultaneously optimize these.